Hello, my name is Skylar McCaw, and welcome to my lab report about circuits and capacitors. The purpose of this experiment is to utilize the principles of energy and current conservation, which includes the loop rule, charge conservation, and steady state, to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure actual values of conventional current, and examine the behavior of ohmic resistors and capacitors. This is the first experiment we will do. It involves setting up a closed circuit with two 1.5 volt batteries, two ammeters, and two resistors, 47 ohms and 100 ohms respectively. Once this has been made to match the picture shown, it's time to predict what the ammeters will say. They read current, so we can use the current equation I equals V divided by R. For this circuit, we know V is equal to 1.5 times 2, which is 3, and the resistors equal the sum of the resistance of the two resistors, which is 147 ohms. 3 divided by 147 is 0.0204 amps. When the circuit is completed and the ammeters read values, they show 0.02 amps, which is the same as what we predicted. You can also try reversing one of the ammeters and seeing that the number shown is now negative of what is previously shown because of this new orientation. Now, remove one of the ammeters and replace it with a voltmeter, and read what it is and the remaining ammeter display. The voltmeter reads 3 volts, which makes sense because the batteries have 3 volts and the resistors has 0. The ammeter reads 0 because the voltmeter does not act as a close to the circuit, so it is still open and the current flowing is 0. Now remove the voltmeter and reclose the circuit with wire. Now we are going to collect readings of potential differences between different points on the circuit using the voltmeter. The points are shown in the diagram in the middle, the values are to the left, and the graph of said values is to the right. Now, add an ammeter parallel to the original attached around the 100 ohm resistor. Notice that now both ammeters read 0.06 up from 0.02. This is because there is less current encountering the 100 ohm resistor due to the additional loop, so resistance is now reduced. In order to keep the equation V equals IR true here, current I must go up to compensate for the drop. With all the information we have, we can calculate the resistance of the elements using Ohm's law, R equals delta V divided by I. This produced a resistance of 47.95 and 102.5 for the resistors and 0 for the wire and ammeter, which makes sense. These values are almost exactly what we set them up for in the resistors. Now for the second portion of the lab, RC circuits. Using the material, make a circuit like the one shown above. Start with a 10 ohm bulb and watch how long it takes for light to go out, the charging. Then remove the battery and time how long it takes again for the light to go out, discharging. Do this again for the 20 ohm bulb. This charging happens because the current flows one way, then slows to 0, then the other way when the battery is removed and goes to 0. The times I recorded for this to happen are listed above. For the last part, we need to calculate the time constant RC. This is done using the equation natural log of delta V divided by delta V naught equals negative T divided by RC. When natural log of delta V divided by delta V naught is graphed against T, the slope of the line is equal to 1 over RC, so it is easy to isolate RC. For my graph, the RC is equal to 3.02. What if this lab was done in real life with a real ammeter? What would be different? The ammeter in the model has no resistance, while the real one would. So the real one would measure values lower if done in person. What if a real battery was used to charge a real capacitor? The charge would be fast, but not instantaneous due to the other parts having small amounts of resistance to them. That is all. Thanks for watching.